Alright, so today we'll talk about the machine cycles, which will also help you understand the how loop works and how that increases the runtime of a computer program. So remember the microprocessor that we always talk about that actually generates some cycles, and the cycles are the one which actually is like the energy of all the energy of the microprocessor, which microprocessor uses to run the instructions. So for an example, if we have a 2 gigahertz microprocessor, that means that it generates 2 to the power 2 times 10 to the 9 cycles per second. Okay. Now every cycle is like a pulse. Remember the uh, the pulse you have seen in electric circuit class, like different types of pulse. Now this is like a square shaped pulse. So pretty much starting from here to all the way up to here is like a full cycle. Now your microprocessor, based on the speed of the microprocessor, it actually generates a lot of cycles like this. It actually keeps generating the cycle, okay, no matter whether you use it or not. Now every instruction uses some of these cycles. Now the point is, let's say for an example, the more cycles a microprocessor generates, that means it is able to run more instructions in every second, because the instructions actually need the cycles to run. Okay, so for an example, if we just write one instruction like this, like LDA pound $25. Now this is an immediate instruction, we all know it, right? This actually takes 2 cycles to be executed. And think about this. Let's say you are running in a microprocessor which is 2 gigahertz, that actually generates 2 gigacycles. 2 to the 10 to the 9, that's like a lot of cycles in 1 second, okay? And this instruction only takes 2 cycles out of that. So think about this microprocessor, that how many instructions it can run in 1 second, right? So okay, now how do I know that this instruction only takes like 2 cycles? We actually know it from our instruction set. If you go to our instruction set, if you look at the column 7, the column 7, we are actually given for every instruction, for every addressing mode, how many cycles actually the microprocessor needs to run that instruction. So for each instruction, for different addressing mode, it actually has different cycles. Now, what exactly we can get from these cycles? We can get several things. Number one, just by knowing these cycles, we can tell how long a program will take to run. This is a very important question, because these days any computer programmer will try to write a program which runs faster than another one, right? So maybe you are trying to solve a problem, writing a program, and now you can write in different manners, different ways. So, but you always want to save the cycles of the microprocessor, so your program runs faster. Okay. So, in this lecture, we'll actually try to calculate the machine cycles given bunch of lines of instructions that we have seen, for this semester, okay, in this whole semester. Now, what exactly we need to know to calculate the machine cycles? Number one, we need to know the addressing modes. We already know it. Just given an instruction, we can tell what is the addressing mode of the instruction. We also need to know the machine cycles required for each instruction. We can know it just from our instruction set, column 7. Pretty straight. We also need to know something called pseudo-op. The pseudo-op is something we probably have never heard until this point, but we'll talk about this one. We'll understand it soon. So that means we pretty much already know about the addressing modes. We also can tell about the machine cycles from the column 7. So we pretty much know all of these. So what is pseudo-op? This is actually set of assembly commands we use to direct the assembly process. You already have actually seen those. Now, this set of assembly commands are not the set of instructions. That means you will not find it in our set of instructions because these are not something specific to the Motorola microprocessor. These are actually for, these are some commands used in general in any assembly program, no matter which microprocessor you are using. See the instruction set that you have all those instructions that actually the Motorola microprocessor support. That's very specific to Motorola. Now these serial ops are not related to the Motorola. You will need it no matter which microprocessor you are using. If you are using any assembly programming with, let's say, Intel microprocessor, with like AMD microprocessor, or with Motorola microprocessor, doesn't matter. You will always need it. And you already have seen it. I'll show you the example, and then you'll know exactly what I'm talking about. And again, this interpreted as a control information to assembler, then assembled into a machine code, because these instructions do not get compiled into a machine code, because these are like, instead of you are trying to give it to the microprocessor, you are actually trying the assembler to do something. Okay, let me show you some of those. I'm sure that you have seen almost all of those. So for an example, one of, I think, the most common one you always use in every program is org. Remember at the very beginning, at the beginning of the program, you always mention, oh, org something, give an address. Think about this command. This is something this doesn't belong to your instruction set. This is something which we always call pseudo op. This specifies, for a specific, this one specifies the location for assembler to deposit the machine code or object code, because you just tell, okay, starting from this address, just the deposit my machine code. Okay, in the same program you can pretty much tell the assembler, okay, now the following lines you just deposit here, and again you say, oh, next following lines you deposit starting from there. So you can pretty much tell your assembler. Now these all you are actually telling to your assembler that, okay, do it there, do it here, but this is not related to a Motorola microprocessor. Okay, so again, here is an example. I'm sure that you already have seen. In every program you have to write it. So program starts from a specific address, right? The following lines. Another one, EQU. I'm sure you have seen this one as well in several programs. This is used to equate a symbolic label to a numeric value. For example, let's say you have plenty of different numbers like addresses, so you will see that we'll be working with ports, not probably in this semester, but in next semester we'll be working with a lot of ports we have with that Motorola, meaning supported by the Motorola microprocessor, in that the kit that we use. So for example, let's say one of the port that we have is port B, So the port B has an address. So anytime if you need port B, you probably don't need to memorize the address of the port B. So what you do is you just write port B EQU then 1004. Now 1004 is the address of the port B. Now how do I know the address of the port B is 1004? This is actually predefined by Motorola. This is not something I can create, okay? This is predefined. Now, what I do is, if I just write a line like this at the beginning of the program, if I just write port B EQU 1004, then every time you write port B, your assembler knows that you are actually trying to write 1004. So it replaces the port B by $1004. Now what is good about this? The good thing is you actually don't have to memorize the number. It's much easier to memorize the port B, compare the address of the port B, because you don't have only port B, you have several other ports, right? And you don't want to memorize all of the addresses when you are writing the program. So that makes it easy. Another one is FCC. This is I'm sure that you probably have seen this as well, right? In I think lab 1 for sure, in even many other labs. This is called form constant character. Now this deposits a text string into the object code. So for an example, let's say this is a string, right? Enter text. Now what you do is you use this as a pointer. For an example, anytime you write text1, your assembler knows that you are referring to this text, this string, okay? And also for sure you use this FCB. I don't think you used FDB, but you used FCB. It's pretty similar because FCB means from constant byte and FDB means from double byte. Now this actually deposit a single byte or word into object code. Now that means if you use FCB, you can just write SB1 FCB A5. That actually means something like this. Think about the high level language you use. Let's say for an example C++. What do you do in the C++? At the very beginning you just say, oh, integer C, okay? That means you define some variable, right? And then later on, or at that point, you just say, okay, C equals to 15. So what you are doing is you are defining a variable C, and then you are assigning a value to C, right? This is pretty similar because this is like SB1 is like a variable which actually holds A5 as a data. Pretty similar, but the good news here is that in the high level language you have a lot of constraints. Let's say for an example, when you just define, let's say, integer, you have to use the integer types of data assigned to your variable, right? You have double, you have long, you have different types of character, right? So you have different types of data types. But here the good news is everything actually is machine bytes, like binary bits, right? So for an example, you are just saying, okay, SB1 is a single byte, okay? Then you are saving A5 there. Now, what exactly this means is SB1 is a memory location. SB1 is referring to a memory location because SB1 is a variable, and that location actually contains a data which is A5. Now you don't know what is the address of SB1 at this point, okay? But you know what data is loaded into SB1 location, meaning the memory location that is assigned to SB1. Same is for DB1. The only difference is SB1 and DB1, meaning like FCB and FDB, because this is a single byte and this is double byte. So meaning 2 bytes. So obviously if you see the 2 bytes, that means this is actually 2 consecutive addresses, okay? But remember, the DB1 always refers to the address of the first byte because it cannot refer the address of 2 bytes simultaneously, right? So it addresses it refers to the address of the first byte, which is C0, okay? We actually don't know what is the address and we don't need to know it, okay, at this point. Now, another one, I'm sure that you have also seen this one, RMB, which is called reserve memory block. This sort of we use to reserve memory byte. This takes an argument or skips or reserve that many bytes ahead in the stream of the output. Because a lot of times what you do is, instead of just using some memory bytes, we reserve memory bytes so that we can use them future in the later part of the program, okay? Remember, I think in the lab 2 you used something like this, RMB, because what you did was you first used you had 2 different numbers and you were doing multi-precision addition with those 2 numbers. So you actually saved some consecutive bytes. So for an example, if you write something like this, RB1 RMB 20, that actually means you are just asking your assembler to reserve the next 20 bytes. So what will happen is your assembler will actually skip the next 20 bytes because it will actually keep those bytes reserved so that you can use them in future. This is again something like defining variable in the high level language, because think about the high level language, you define the variables at the top, right? And a lot of times you don't probably use the variables right away. You just say, oh, integer, C, and then character X, and you just, do this, right? So what happens is your compiler reserve, some you exactly don't know where it reserves is. In the low level language, you can exactly tell where things are happening. So because you have more knowledge about the machine and memories, right? So you can tell where those 20 bytes are reserved, but there will be 20 bytes, a block of bytes which will be reserved. Now this number you can do whatever you want, right? You can just reserve 3 bytes. You can just say, oh, I want to reserve 100 bytes, based on pretty much how many bytes you need. So you already have seen plenty of pseudo ops that we used in our programs. We'll talk about the same pseudo ops again, but let's first try to see how can we calculate machine cycles given a very small and simple code. Now we have three lines of instructions here. Now how many machine cycles are required to execute the following code segment? And how can I tell this? Now first I need to know, again, the addressing mode of each line. So from the addressing mode, what I can do is, all I have to do is go to my instruction set, look at this instruction and look at the addressing mode. For an example, the first instruction that I have is LDAA. If I go to LDAA, check the column 7. Make sure you understand this, okay? So take your instruction set and take a look at the LDAA and look at the column 7 for LDA and look at the machine cycles given for the immediate type of instruction. If your instruction is immediate, for LDA, your machine cycle will be 2 cycles. Do you see it? Column 7. Now the next instruction is direct, right? So check the ADDA direct mode. You'll find the machine cycles in the column 7. ADA should be in the first page, right? Do you see the machine cycle is what? 3 cycles. And the last instruction you have is STAA 00$0, so which is like an extended instruction. Now if I go to my STAA extended mode, you will find the machine cycles which is 4 cycle, right? Column 7. So I actually got this number from here. So all I have to do is just for these 3 lines to calculate the machine cycles, all I have to do is just add the cycles. Pretty simple, okay? Now I have 9 cycles. So given these lines, just based on the addressing mode, I can directly tell how many cycles of the microprocessor you need to run this, 3 lines of instruction. Now the machine cycles are actually very important because just from the machine cycles you can tell how long it will take. Because if you have pretty similar 3 lines but using different instructions, you might need like much more cycles than these 3 lines. Then from there you can definitely tell those 3 lines will take much longer than these 3 lines to run. Now there are some even instructions which takes much more cycles. Can you check how long the MUL instruction takes from your instruction set? There is an instruction MUL, right, which actually does the multiplication, which is an inherent instruction that has only one mode. How many cycles? 10 cycles. So think about that one. So that single instruction even take longer than these 3 lines, because these 3 lines only take 9 cycles and MUL itself takes 10 cycles. So in the computer language we say, oh, this instruction is more expensive, because the more cycles it takes, you probably don't want to use that instruction more frequently unless you need it. There are a lot of different ways you can avoid some instruction. For an example, let's say you are just doing 2 times 2, or you can do just 2 plus 2. It actually give you the same answer, right? That's what I'm saying. 2 plus 2 and 2 times 2 will give you the same answer. Now, which instruction you select? Do you just try to add it, or you just try to multiply it? You will definitely try to add it, because if you add it, it will take less cycles than if you multiply. because MUL instruction takes more instructions. So think about this situation. So if you need more about the cycles, you can carefully select your instructions so that your program runs faster than a different alternate one. Okay. Now let me show you something again about the machine cycles, where we have also something about the zero up. Now, so for an example, let's say you have this line number 3 and you are trying to calculate the machine cycles. Now the catch is, if you look at the line 3 carefully, look at this A1 label. Now from here we cannot tell what is this line. I'm saying, is this an immediate instruction, or is it direct or extended? We don't know it. Now here is the problem. If you don't know what is the addressing mode, you cannot calculate the machine cycle. Now how can I tell what is the addressing mode? Now think about this label. This is A1, right? Which actually is here. Now do you see there is a zero up here? Now from this zero up you can tell this A1 actually holds an address. A1 means an address which holds 48, right?